Regression. The key takeaways will be what you need to implement. That is the key equations you need in order to implement gradient descent for logistic regression. But in this video, I want to do this computation using the computation graph. I have to admit, using the computation graph is a little bit of an overkill for deriving gradient descent for logistic regression. But I want to start explaining things this way to get you familiar with these ideas so that hopefully it'll make a bit more sense, a bit of an overkill for deriving. But in this video, I want to do this computation using the computation graph. I have to admit, using the computation graph is a little bit of an overkill for deriving gradient descent. To start explaining things this way to get you familiar with these ideas so that hopefully it'll make a bit more sense to talk about full-fledged neural networks. But so that, let's dive into gradient descent for logistic regression. To recap, we had set up logistic regression as follows. Your predictions y hat is as follows, where c is that. And if we focus on just one example for now, then the loss with respect to that one example is defined as follows, where A is the output of logistic regression and Y is the ground truth variable. So let's write this out as a computation. And for this example, let's say we have only two features, x1 and x2. So in order to compute C, we need to input W1, W2, and B in addition to the feature values of x2. So these things in a computation graph get used to compute C, which is W1 x1 plus W2 x2 plus B. Draw a rectangular box around that. And then we compute y hat or A equals sigma of Z. That's the next step in the computation graph. And finally, we compute L, A, Y, and I won't copy the formula again. So in logistic regression, what we want to do is to modify the parameters W and B in order to reduce this loss. Describe the four computation steps of the actually compute over loss. Go to an example. Now let's talk about how you can go backwards to compute the derivatives. Here's a cleaned up version of the diagram. Because what we want to do is compute derivatives, respect to this loss, the first thing we want to do going backwards is to compute the derivative of this loss with respect to script out there with respect to this variable a. And so in the code, you just use TA, right, to denote this variable. And it turns out that if you are familiar with calculus, you know that this ends up being negative y over a. Over 1 minus a. And the way you do that is you take the formula for the loss, and if you put calculus, you can compute the derivative with respect to the variable lowercase a, and you get this formula. But if you're not familiar with calculus, don't worry about it. Provide the derivative formulas you need throughout this course. So if you're an expert in calculus, I would encourage you to look up the formula for the loss from the previous slide and try to respect to calculus, but if you don't know enough calculus to do that, don't worry about it. Now, having computed this quantity dA, the derivative of the final output variable with respect to a, you can then go backwards. And it turns out that you can show dz, which this is the Python code variable name. This is going to be the derivative of the loss with respect to c. For L, you can really write the loss, including a and y, explicitly as parameters are known to either type of notation is equally acceptable. We can show that this is equal to a minus y. Just a couple comments only for those of you that are expert in calculus. If you're not expert in calculus, don't worry about it. But it turns out that this, right, dl dz, this can be expressed as dl dA times dA dz. And it turns out that dA dz, this turns out to be a times 1 minus a, and dl dA we have previously worked out over here. And so if you take these two quantities, dl dA, which is this term, together with dA dz, which is this term, and just take these two things and multiply them, you can show that the equation simplifies to y. So that's how you derive it. And this is really the chain rule that I briefly alluded to. Okay, so feel free to go through that calculation yourself if you are knowledgeable about calculus, but if you aren't, all you need to know is that you can compute dz as a minus 1. I've already done that calculus. Step in propagation is to go back to compute how much you need to change w and p. So in particular, you can show that the derivative with respect to w1, and in code we'll call this dw1, that this is equal to x1 times dz, And then similarly, dw2, which is how much you want to change w2, is x2 times dz, and dp is equal to dz. So if you want to do gradient descent with respect to just this one example, what you would do is the following. You would use this formula to compute dz, and then use these formulas to compute dw1, dw2, and dp, and then you perform these updates. W1 gets updated as W1 minus learning rate alpha times dW1. W2 gets updated similarly, and B gets set as B minus the learning rate times dP. And so this would one step upgrade with respect to a single example. So you see how to compute derivatives and implement gradient descent for logistic regression with respect to a single training example. But to train your logistic regression model, you have not just one training example, you have an entire training set of M training examples. So in the next video, let's see how you can take these ideas and apply them to learning not just from one example, but from an entire training set. My training sets of M training examples. So in the next video, let's see how you can take these ideas and apply them to learning not just from one example, but from an entire training set. You saw how to compute derivatives and implement gradient descent with respect to just one training example for logistic regression. Now we want to do it for m training examples. To get started, let's remind ourselves of the definition of the cost function. Okay, cost function WP we should care about is something like this 1 through m. Uh, the loss, the algorithm output AI on the example Y, where AI is the well, prediction on the I training example, which is sigma of Ci, which is equal to sigma of W transpose Xi plus P. Okay, so what we showed in the previous slide is for any single training example, how to compute the derivatives um, when you have just one training example. W1, dW2, and dP, with now the superscript I to denote the corresponding values you get if you were doing what we did on the previous slide, but just using the one training example, xi, yi, excuse me, missing an I there as well. So now you notice the overall cost function is the sum, was really the average because of the 1 over m term of the individual losses. So it turns out that the derivative with respect to say W1 of the overall cost function is also going to be the average of derivatives with respect to W1 of the individual loss terms. But previously, we had already shown how to compute this term as, say, dw1 I, right, which we, on the previous slide showed how to compute this on a single training example. So what you need to do is really compute these derivatives as we showed on the previous training example and average them. And this will give you the overall gradient that you can use to implement gradient descent. So I know there was a lot of details, but let's take all of this up and wrap this up into a concrete algorithm. So into what you should implement to get logistic regression gradient descent working. So here's what you can do. Let's initialize j equals 0, dw1 equals 0, dw2 equals 0, db equals 0. And what we're going to do is use a for loop over the training set and compute the derivatives with respect to each training example and then add them up, right? So here's what we do. For I equals 1 through m, so m is the number of training examples, we compute zi equals w transpose xi plus b. The prediction ai is equal to sigma of zi. And then, let's add up j. J plus equals yi log ai plus 1 minus yi log 1 minus ai. And let's put a negative sign in front of the whole thing. And then as we saw earlier, we have dzi, right, is equal to ai minus yi, and dw gets plus equals x1i dzi, dw2 plus equals xi2 dzi. When I'm doing this calculation, assuming that you have just the two features, so that n is equal to 2. Otherwise, you do this for dw1, dw2, dw3, and so on. dp plus equals dci. And I guess that's the end of the for loop. And then finally, having done this for all m training examples, you would still need to divide by m because we're computing averages. So dw1 divided equals m, dw2 divided equals m, dp divided equals m in order to compute averages. And so with all of these calculations, you just computed the derivatives of the cost function j with respect to each of your parameters w1, w2, and p. Just a couple of details of what we're doing. We're using dw1 and dw2 and dp as accumulators, right? So that after this computation, dw1 is equal to the derivative of your overall cost function with respect to w1. And similarly for dw2 and dp. So notice that dw1 and dw2 do not have a superscript I because we're using them in this code as accumulators to sum over the entire training set. Whereas in contrast, dzi here, this was dz with respect to just one single training example. So that's why that had a superscript I to refer to the one training example I that's computed. And so having finished all these calculations, to implement one step of gradient descent, you would implement W1 gets updated as W1 minus the learning rate times D. W1, W2 gets updated as W2 minus learning rate times DW2, and B gets updated as B minus learning rate times DB, where DW1, DW2, and DB were, as computed. And finally, J here would also be a correct value for your cost function. So everything on this slide implements just one single step of gradient descent, and so you have to repeat everything on this slide multiple times in order to take multiple steps of gradient descent. In case these details seem too complicated, again, don't worry too much about it for now. Hopefully all this will be clearer when you go and implement this in the programming assignment. But it turns out there are two weaknesses with the calculation as we've implemented it here, which is that to implement logistic regression this way, you need to write two for loops. The first for loop is a for loop over the n examples, and the second for loop is a for loop over all the features over here. Right. So in this example, we just had two features, so n is equal to 2 and x equals 2. But if you have more features, you end up writing dw1, dw2, and you have similar computations for dw3, and so on down to dwn. So it seems like you need to have a for loop over the features over all n features. When you're implementing deep learning algorithms, you find that having explicit for loops in your code makes your algorithm run less efficiently. And so in the deep learning era, we move to bigger and bigger data sets. And so being able to implement your algorithms without using explicit for loop this way, you need to write two for loops. The first for loop is this for loop over the n examples, and the second for loop is a for loop over all the features over here. Right. So this example, we just had two features, n is equal to 2 and x equals 2. But if you have more features, you end up writing dw1, dw2, and you have similar computations for dw3, and so on down to dwn. So it seems like you need to have a for loop over the features over all n features. When you're implementing deep learning algorithms, you find that having explicit for loops in your code makes your algorithm run less efficiently. And so in the deep learning era, we move bigger and bigger data sets. And so being able to implement your algorithms without using explicit for loops is really important and will help you to scale to much bigger data sets. So it turns out that there are certain techniques called vectorization techniques that allow you to get rid of these explicit for loops in your code. I think in the pre-deep learning era, that's before the rise of deep learning, vectorization was a nice to have. So you could sometimes do it to speed up your code and sometimes not. But in the deep learning era, vectorization, that is getting rid of for loops like this and like this, has become really important because we're more and more training on very large data sets, and so you really need your code to be very efficient. So in the next few videos, we'll talk about vectorization and how to implement all this without using even a single for loop. So with this, I hope you have a sense of how to implement logistic regression, gradient descent for logistic regression. Things will be clearer when you implement the program exercise. But before actually doing the program exercise, let's first talk about vectorization so that you can implement this whole thing. Implement a single iteration of gradient descent without using any forms.
So this is end of today's report.